Imagine looking up at the stars and asking, is there another Earth out there? Could we ever live somewhere else? As of the year 2025, the answer is both inspiring and sobering. No planet has been found that offers what Earth does: liquid water on the surface, breathable oxygen in the air, and the ability for humans to live without complex technology. Let us begin with what scientists have actually discovered. Astronomers have found more than 5,600 planets orbiting distant stars called exoplanets. Some of them are rocky, some are the right distance from their star, and a few may even have liquid water. These are called potentially habitable planets. But here's the catch: they are all very, very far away. The closest promising world is Proxima b, which orbits the star Proxima Centauri. It is about 4.24 light years from Earth. That is around 40 trillion kilometers. If you traveled as fast as the Voyager 1 spacecraft, the fastest object humans have ever launched, it would take more than 76,000 years to get there. Now, let us look at other top candidates. The TRPPIST-1 system, about 39 light years away, has several Earth-sized planets in the right zone for liquid water. Kepler 442b is one of the most Earth-like we've seen, but it is over 1,200 light years away. At present, we can detect their size and maybe their temperature, but we cannot say for sure if they have oceans, oxygen, or life. So how far can we realistically go? The farthest humans have traveled is just under 400,000 kilometers. To the moon, the farthest any human-made object has gone is Voyager 1, now more than 24 billion kilometers away. Even our fastest rockets cannot take humans beyond our solar system within a lifetime. Here's our future ideas, like laser-powered microspacecraft that could reach nearby stars in just 20 years, but only for sending tiny probes, not people. Nuclear propulsion might help, but it is still centuries away from supporting human travel over interstellar distances. Since we cannot reach another Earth-like planet anytime soon, scientists have suggested other ideas: terraforming or transforming a hostile planet to resemble Earth. Mars, for example, has ice, a day similar to ours, and is relatively close. But to make it livable, we would need to create atmosphere, protect against radiation, and warm the planet, an enormous challenge. Venus is too hot, with crushing pressure and toxic clouds. Moons like Europa or Titan might have subsurface oceans, but we would need to live in pressurized habitats under thick ice or in artificial domes. So far, there is no known place beyond Earth where a human could step outside and breathe without a suit. Could we build our own artificial Earth in space? Some scientists imagine giant rotating habitats called NeillCylinders that create artificial gravity and support ecosystems. But this would require new technologies for recycling air, water, and food, closed-loop systems that do not yet exist on a large scale. Now, what about the basic ingredients for life, water and oxygen? Water is fairly common in space. We found ice on Mars, in the rings of Saturn, and on distant exoplanets as vapor or frost. But oxygen is another story. While we have seen hints of it in some atmospheres, we have not yet detected it alongside other signs of life, like methane or ozone, in a combination that suggests a truly Earth-like biosphere. Telescopes like the James Webb Space Telescope, or JWST, are now searching for these signs. Future missions like LUVOIR could look even deeper. Scientists are watching for the biosignature cocktail: oxygen, ozone, methane, and water vapor, all balanced in a way that suggests something is breathing and living there. But here is the hard truth. Even if we find a perfect Earth twin, we do not have the means to go there, not in this century. We might send robotic probes, we might build habitats on the moon or Mars, but no planet has yet been found where you could walk outside and take a breath. Ask yourself, if Earth is the only world where we can live freely, should we not treat it with more care? Every future planned terraforming, colonizing, or star travel requires technology we are only beginning to understand. For now, Earth is not only our home, it is our only safe harbor. Would you like a simple chart comparing Earth, Mars, and the best exoplanet candidates based on habitability and distance? Earth is the only known planet with stable liquid water on its surface, a nitrogen-oxygen atmosphere, and a magnetic field that protects life from solar radiation. The atmospheric pressure, temperature range, and chemical balance are finely tuned to support complex biology. Earth's ecosystems provide not only oxygen and food, but also microbial symbiosis that maintains ecological homeostasis. The planet's geologic activity and carbon silicate cycles stabilize the climate over long timescales. No known planet matches all these parameters simultaneously. Earth's oxygen concentration, tilde 21%, and atmospheric pressure, tilde 118, are just right for human metabolism and combustion processes. Earth is like a perfectly calibrated life support machine, unmatched by any known device in the cosmos. Astronomers use the concept of a habitable zone, the range of distances from a star where liquid water could exist, to identify potentially Earth-like exoplanets. These planets must be rocky, Earth-sized, and ideally orbit stable stars. To date, over 5,600 exoplanets have been discovered and dozens are in the habitable zone. However, most of these candidates lie tens to thousands of light years away and are detected via indirect methods. Their actual surface conditions remain largely unknown due to limitations in telescope resolution. Proxima b orbits in the habitable zone of Proxima Centauri, but may be bombarded by flares from its red dwarf star. Finding a planet in the habitable zone is like spotting a house in the right neighborhood without knowing if it has clean air, plumbing, or even walls. Humanity's space travel has so far extended only to the moon, tilde 400,000 K, and our spacecraft cannot yet carry humans beyond that range safely. The Voyager 1 probe, launched in 1977, is the farthest human-made object, but still only 0.0025 light-years away. Chemical rockets are too slow for interstellar travel. Even reaching Proxima b would take over 70,000 years at current speeds. Advanced concepts like laser sails or fusion propulsion remain theoretical or only applicable to unmanned probes. Thus, crude interstellar travel remains far outside current technological capabilities. Breakthrough Starshot proposes sending gram-scale probes to Proxima Centauri using lasers, but no human crew can travel that way. Our fastest spaceships are like rowboats compared to the distances required. Great for crossing a pond, but not an ocean. To determine whether a planet is truly habitable, scientists look for biosignature gases like oxygen, ozone, methane, and water vapor in exoplanet atmospheres. These can be detected via transit spectroscopy, measuring starlight filtered through a planet's atmosphere. However, current telescopes lack the resolution to confirm Earth-like atmospheric composition. New missions like the James Webb Space Telescope, JWST, and planned missions like LUVOIR aim to close this gap. Until then, we can only infer potential habitability from indirect metrics such as planetary mass and orbit. JWST is now beginning to analyze atmospheres of planets like TRAPPIST-1e for signs of water or CO2. It is like hearing a muffled voice through a wall. You know someone is speaking, but not what they are saying. Terraforming proposes modifying a planet's climate, atmosphere, or ecology to make it Earth-like. Mars is the prime candidate due to its proximity, day length, and surface gravity, but it lacks a magnetic field and has very low atmospheric pressure. Terraforming would require generating an artificial greenhouse effect, releasing CO2, importing ammonia, or deploying orbital mirrors. Venus, despite its Earth-like size, has a toxic, high-pressure atmosphere and runaway greenhouse conditions, making it an even harder challenge. These efforts would require centuries of engineering and planetary-scale technologies we do not yet possess. Elon Musk proposed terraforming Mars by detonating nuclear bombs over the poles to release CO2 and warm the planet. An idea widely criticized as unrealistic. Terraforming is like trying to turn a desert into a rainforest using only a hairdryer and a garden hose. Some moons in our solar system, like Europa, Titan, and Enceladus, have subsurface oceans and organic chemistry that intrigue astrobiologists. However, none have breathable air, and all require enclosed pressurized habitats for human survival. Technologies such as biodomes, radiation shielding, and artificial gravity would be needed to sustain life. Alternatively, space colonies like NeillCylinders, rotating space habitats, simulating Earth-like conditions, have been proposed. These two remain theoretical due to massive engineering challenges and unproven long-term sustainability. NASA's Artemis program aims to build a long-term habitat on the moon to test life support systems for future Mars missions. Living on these moons is like surviving inside a sealed submarine, safe only as long as the air, food, and power systems work perfectly. Liquid water is a key ingredient for life as we know it, and it has been detected on several solar system bodies and inferred on many exoplanets. However, oxygen is much rarer and more biologically significant. It is often a product of photosynthesis, not a primordial atmospheric gas. Oxygen-rich atmospheres have not yet been directly detected on any exoplanet. Non-biological processes can also create oxygen, so its detection must be paired with other gases like methane to be a biosignature. Earth's unique atmosphere likely developed through a long interplay of microbial activity, plate tectonics, and climate regulation. The detection of water vapor in the atmosphere of K2-18b suggests potential habitability, but its dense atmosphere may be hostile to life. Water may be common in the universe, but oxygen is like a rare spice. It suggests the presence of a sophisticated cook. Even if we reach another world, human survival depends on more than air and water. It includes mental health, microbiomes, gravity adaptation, and fertility. Microgravity affects bone density, cardiovascular health, and neural function over time. Radiation exposure outside Earth's magnetosphere increases cancer and genetic mutation risks. Isolated environments can lead to psychological stress, depression, and conflict among crew. Thus, long-term off-Earth survival demands solving biological, social, and engineering challenges together. Astronauts aboard the ISS exercise daily to reduce bone loss and psychological stress in microgravity. It is like trying to transplant a coral reef to a desert. You need to recreate not just the water, but the entire ecosystem and climate. As of 2025, no planet other than Earth supports human life without extensive technological mediation. The best exoplanet candidates are light years away, unreachable with today's propulsion. Terraforming or colonizing the moon or Mars will take centuries of development and will still fall short of Earth's comfort. Space telescopes and astrobiological missions continue to expand our knowledge of the cosmos, but practical human migration remains a distant dream. For the foreseeable future, preserving Earth is the most critical mission for human survival. Despite decades of exploration, the only sustainable human habitats are still on Earth or in Earth orbit. Looking for a new Earth is like looking for a new heart. You may explore replacements, but you must protect the one you have.